Hello, my name is Elizabeth Terra, and I'd like to talk to you today about dynamic simulation of a double pipe heat exchanger. I've enjoyed the studying of fluid mechanics, thermodynamics, and heat transfer for several semesters now here at UT Tyler at Houston. I do plan on continuing my education in this field of thermodynamics as I pursue a master's degree. I chose to use a heat exchanger not just for its simplicity, but the fact that it's had a strong impact on the energy industry for several years, several decades at least. And with its simplicity of just a heat exchanger is just a device that has transferred heat from one liquid to another by direct or indirect contact. And a type of tube of a thermoconducting element is being used to separate the two fluids and allow the transfer of heat from one fluid to another without mixing. Now, just a simple double pipe heat exchanger consists of those concentric pipes, and is commonly used in applications involving relatively low flow rates and high temperatures or pressure, for which they are well suited for. And again, as I stated, that's why they continue to be in use even as of today. Now, as far as the history of heat exchangers, some of the earliest publications I was able to find was dated back as far as 1912, where they began analyzing double pipe heat exchangers, and for several reasons of analyzing double pipe heat exchangers and understanding the overall process. Now, with its simple design and its significance of understanding, of course, implementing the understanding of your fluid properties, I felt it would be ideal to kind of create a model that would kind of take into account for the variations of like heat transfer with respect to the fluid flow rates and temperature, and really have an ability to kind of almost predict that it's transient operations conditions and then getting that into a steady state condition. Now, by doing this, I've found that you're able to reduce or minimize the cost of heat exchanger, kind of like a network synthesis. And even though this is difficult to sometimes analyze as a whole, but what it does is it really gets you to focus on two of its kind of most important parts in its desirability, and that's its flexibility, and it's also its controllability, which really got me to why I chose this as that control dynamics of the double pipe heat exchanger and using kind of a simulation tool. And so then what that did was I needed to pretty much, in a sense, derive a transfer function, and it can be taken as a first order system plus dead time, and also to establish kind of like the effect of the step change in flow rates of hot water as it's analyzed, and also observe the effect of the temperature on the cold water, and found, as far as how to implement that and how it can be regulated. And then, of course, always, wanting to be more accurate in controlling the overall processes, and doing that as a steady state and dynamic simulation of the double pipe heat exchanger, able to really study and simulate the results for this step change in regards to the two fluid mechanics, or fluid properties, I should say. So anyways, a G is stated here as your transfer function, and that TD is your transport delay, and of course K is your process gain. And this is the most commonly used model to describe dynamics of pretty much chemical processes, like I stated earlier, in the energy industry. And with that, and be able to do this in MATLAB, you're able to kind of be able to remove some of the problems that you would see if you did not have a control system, the problems of an overshoot, maybe even a considerable time delay, and or also it shows that it almost kind of creates an inverse response. And so by implementing a proportional integral derivative, a PID controller, you're able to reduce all those. And so for this simulation, I was going under the controls of designing it under a closed loop system. And by simulating this in MATLAB and using, which I use is the tune, have it tuned under the Cohen-Kuhn tuning rules, and able to analyze this. And for here, I've just kind of simulated the possibility of how this might look or how this might be in a block diagram. And so the whole point of choosing this is to really just have a better understanding of the applications of simulating a PID controller, even as simple as on a heat exchanger, double pipe heat exchanger, and just analyzing and deriving a step function for both the cold and the hot fluid. And then my overall goal is to be able to explain this simulation in great detail with a better understanding of it, and also to understand how the whole plant process can become stable and unstable because you are dealing with temperatures and pressures. And so that's my goal for this project for system dynamics. And I appreciate your time. Thank you.